Today we're going to review motion graphs from grade 11. So here's the first graph to talk about. First of all, you want to read the axes, so see what the axes are labeled with. So on the vertical axis, I see a D with the harpoon. That's position. And on the horizontal axis, I have T in seconds, so that's time. So this is called a position time graph. And you need to know certain things about a position time graph. So one thing you need to know is how the shape of the function on a position time graph, what it tells us about the velocity, how fast it's going. So we're going to take this graph section by section. So the first section would be this horizontal segment. And that section extends from 0 to 2 seconds. And what is going on during that section? Well, if we read the vertical axis, it's saying that the position is -10, and it's just staying at -10. The function is just staying constant at -10. So it's actually at rest. Okay, that's what we're going to say. This is at rest, at a position of -10 meters north. So horizontal segment means it's at rest. Okay, what about the next section? So this straight segment from 2 to 3 seconds, and it continues on from 3 to 4 seconds, but perhaps something special happens right at 3 seconds, so we'll talk about it. So what's going on in this section? Well, it's no longer at rest. It's moving. So the position starts at -10, and then it gradually moves towards 0. It gets to a position of 0, and then it keeps going, and it goes all the way up to a position of +10. So I would say that the object is moving. But how is it moving? Is it herky-jerky moving, or is it a nice smooth motion? So when you have a straight line segment on a position time graph, that actually represents a constant velocity. Okay, when the slope is constant, then the velocity is constant. So it's a nice smooth motion. Furthermore, we can calculate the value of the velocity based on how steep that line is. We call that the slope of the graph, and you can calculate it with rise over run. So I'm just going to write on the right-hand side here. So 0 to 2 seconds. We were at rest at a position of -10. Meters north. You get the units and the direction based on reading the axes there. Okay, and now 2 to 4 seconds. Okay, so 2 to 4 seconds. Constant velocity. And I want to give a number for it. I want to give a number for that constant velocity. And that number is going to be the slope of that line segment. So I'll calculate the slope here on the graph. The slope is rise over run. And the rise, it goes from -10 to +10. So the rise is 20 meters north. And the run, it went from 2 to 4 seconds. So that's a run of 2 seconds. So 20 over 2 is 10 meters per second north. Okay, so constant velocity of 10 meters per second north. And it ends at a position of 10, +10. So I guess a sub point here is at the instantaneous time of 3 seconds. What happened? The graph crossed 0. So in a position time graph, a position of 0 means it's right at the reference point. It's right at the point where we're marking our positions from. So at t equals 3 seconds, it passes the reference point. So that's just an extra detail I thought was interesting to include. All right, so now we need a new section here. So now the graph starts to curve. It curves. I'm gonna stop there for now at 6 seconds. Because the graph is curving in a certain way from 4 to 6 seconds, but then it seems to come back down after from 6 to 8 seconds. So I'm going to treat those as two different things. I'm going to use two different colors here. Okay, so I'm going to start from 4 to 6 seconds. So that curve, the position is still changing. Okay, the position is at 10 seconds, and then it's still going up, but just not as quickly. It eventually gets up to just less than 15, so maybe 14. Yeah, so it is still going north, but it's not at a constant velocity this time. So it's accelerating, and in this case, it's slowing down. So when a curve is getting less and less steep, as this one is, then it's slowing down. So it's still moving north. It's still continuing to get higher on this axis, but it is slowing down because it's getting less steep. Okay, so I'll write that down on the right-hand side here. So from 4 to 6 seconds, moves north. But is slowing down. I'm going to say what maximum position it reaches. So it reaches a position of 14. At the 6 second mark. Okay, so that's from 4 to 6 seconds. And now in green, it's curving again, but now it's going down. Okay, so it's going back towards the reference point. Okay, so it's moving, I would say moving south, the opposite direction. And it's not a straight line, it is a curve, so it's not going at a constant velocity. This one is speeding up. And first of all, logically, it kind of has to, because first of all, you just turned around. Like, you were going north, and then now you're going south. So at some point, you had to turn around, and so you had to come to a stop. That actually happens right at the 6 second mark. It came to an instantaneous stop. And you can tell if something comes to an instantaneous stop if the tangent line is horizontal. If I draw a tangent line here, it's horizontal. I'm actually going to add that into my notes here. Object instantaneously stops at t equals 6 seconds. It's not a prolonged stop, it's just for an instant. Then it turns around, starts moving south, and is speeding up again because the curve is getting steeper. So I'll write that down. 6 to 8 seconds. Moves south and is speeding up. Okay, and finally, the last section I'll use yet another color here. The last section, the object, I would say, is still going south. It goes all the way down to 0. Okay, it moves south to 0. Now, is it speeding up, slowing down, or is it at a constant velocity? Well, this line segment is straight. So if it's a straight line segment, it's a constant velocity. Okay, something happened with my pen there. And I can calculate the slope of this last segment. It's rise over run again. So the rise is negative this time. And it looks like, so it went from about, let's say, 12 to 0. So the slope is negative 12 meters north. And the run went from 8 to 9 seconds. So that's just 1 second. So the slope is negative 12 meters per second north. Alternatively, you can say 12 meters per second south. Okay, so in my notes, I will say from 8 to 9 seconds, moves south at a constant velocity of 12 meters per second south. Okay, so now I do have a seemingly random line drawn right at t equals 5 seconds. I know it's a little messy at this point, but I'm going to highlight it. Okay, so I drew this seemingly random line at t equals 5 seconds. So why did I draw that line there? What am I trying to get at? So one other point you may have learned in grade 11 is that you can find the instantaneous velocity of the object by drawing a tangent line to the function and then calculating the slope of the tangent. Okay, so I did that. I drew a tangent line right at this, just grazing the graph at the 5 second mark. And that's the slope of that line is supposed to represent instantaneously how fast the object is going at 5 seconds. So I'll write that down at the bottom here. A tangent line is drawn at t equals 5 seconds. The slope of a tangent line gives instantaneous velocity. Okay, so I'll calculate the slope of the black line here. Rise over run. So, well, I'm gonna just estimate here. So from the beginning to the end, it rose. So it's at about 9, and it went up to about 17. So from 9 up to 17, I'm just gonna write 17 minus 9. And then the run, it started at about 2.3 and went up to about 7.3. So I'm going to say 7.3 minus 2.3. This is just an estimate here. Okay, so that would be 8 over 5, and that would be 1.6 meters per second north. Okay, so what I'm trying to say is that, so therefore, the instantaneous velocity at t equals 5 seconds is about, so I'll use this approximately symbol, this little tilde here, 1.6 meters per second north. All right, so those are the main things you should have learned about a position time graph from last year. Basically how to tell if the object is at rest, moving north or versus south, moving at a constant velocity versus slowing down versus speeding up. And also that by calculating slopes, you can get the numbers for the velocity. And so that's a lot there. Okay, so this slide can kind of be a summary slide. If you see these shapes on a position time graph, what's physically happening? So I would call this a qualitative slide. Like it's talking about qualitative information here. So if you see a horizontal line, the object is at rest. If you see a straight line, the object is at constant velocity. If the line is traveling with a positive slope, then it's moving in the forward direction or the positive direction. And if it has a negative slope, it's moving in the negative direction. So constant velocity in positive direction. And then constant velocity in the negative direction. Okay, then if you have curves, curves mean it's either speeding up or it's slowing down based on if it's getting steeper or getting less steep. So the first one, it's getting steeper. So it's speeding up. You also want to know which way it's going. So if the function is increasing, the function is getting higher, it's moving in the positive direction. Moving in the positive direction. And speeding up. The second one, it's still moving in the positive direction. So the function is still getting higher. In the previous example, we would have said it was still moving north. But this time, the line is getting less steep. Okay, the slope is getting lower and lower, so it's slowing down. And then the last one here, this time it's moving in the negative direction. The function is getting lower. Now is this speeding up or slowing down? We look at the slopes, very steep slope to start, very shallow slope to end. So it would be slowing down. Okay, so that's an important skill to be able to describe qualitatively what's going on with the object based on the shape of the graph. Next, we're going to draw a matching velocity time graph. So this is the same graph from before, and you might have to draw a matching velocity time graph. So to do that, I'm going to first draw some axes. This will be labeled time in seconds. Now this will be labeled velocity. So V harpoon, and the units would be meters per second for velocity. And the direction, I'm just going to copy the direction in the position time graph, so north. I'm going to go from 1 to 9 to match the time of the other graph. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then section by section, I'm going to basically try to remember what I said from before and draw it out. So the first 2 seconds, it was at rest. So when it's at rest, it's simply a velocity of 0. Okay, at rest is the velocity of 0. So this is the first 2 seconds. Okay, from 2 to 4 seconds, we said it was a constant velocity, and we calculated the number, and the number was 10. Okay, the number was 10. So I'm going to put a mark here for 10, and it's going to be a constant velocity of 10. Okay. Now I'm drawing open circles at the endpoints at 2 seconds because I don't actually know what the velocity is right at 2 seconds. Like right at that point, what's the velocity? It makes a really, really sudden change. It makes a sharp point in the graph. We call those points cusps. And when you have a cusp, it's not a smooth transition. So I actually don't know what the velocity should be exactly at 2 seconds. So I'm going to put open circles in my graph to represent not actually knowing the value. All right. Next, from 4 to 6 seconds. So from 4 to 6 seconds, it was slowing down. And at the 6 second point, this was a really special point. What happened at the very peak of that curve, it was instantaneously at rest. It was instantaneously at rest, which means it has a velocity of 0. Okay, at rest means you have a velocity of 0. So I'm going to put a mark at 0 at the 6 second mark. And I need to get from here, from the 10 meter per second, down to a 0 meter per second. So I'm simply going to just connect it with a straight line there. That represents slowing down. It slows down from 10 to 0 meters per second. Okay, now from 6 to 8 seconds, now it starts to have a negative velocity. Oh, by the way, I drew closed circles at these points. Like I filled in the dots. I didn't leave them open. That's because I know for sure what the velocities are. At the 4 second mark, there is no cusp. It's actually a nice smooth transition. So it is, I know for sure that it's instantaneously at 10 meters per second. I don't have to guess or anything. It's for sure 10 meters per second. So I can fill in my dot at a value of 10. Similarly, at the 6 second mark, I know for sure that it's a velocity of 0 meters per second. So I can color in my dot at the 6 second mark. Okay, so we'll keep going. From 6 to 8 seconds, it's slowing down. So, no, sorry, it's speeding up. But now it's moving backwards. It's moving in the south direction. So my graph is going to cross the axis and start going into negative values. Okay, start going to negative velocities because I'm going south. I don't exactly know where the line should end up. I didn't calculate anything, so I'm just going to have it end at a random spot there. Okay, next, from 8 to 9. Here I have a cusp again. So it's not a smooth transition. So that's another reason why I put an open dot at the 8 second mark on my graph there. But I did calculate this slope here, and I calculated it to be negative 12. So I'm gonna make a label at here, negative 12. And I had a constant velocity of negative 12. So that's how I'm going to end the graph. I'm going to have a horizontal line staying at negative 12. And that would be the matching velocity time graph for my position time graph. Basically, you have to calculate a lot of slopes to figure out the velocities at a lot of different places. And then you just draw those numbers on the velocity time graph. Okay, I'll keep going. Analyze this graph. So this graph is different. You should need to look at the axis, and I see a V with the harpoon on my vertical axis. So this is a velocity versus time graph. Time is on the horizontal axis. So the graph is telling me velocity, not position. So it turns out to be a very, very different. What's going on during the first 2 seconds here? Well, if you think it's at rest, you would be incorrect. This is staying. This is a constant -4 meters per second. We have a constant -4 meters per second north. So it's moving because meters per second, that's a velocity unit. So it's moving at a constant -4 meters per second north. So I'll write that down. From 0 to 2 seconds, constant velocity of -4 meters per second north. Or alternatively, you can say +4 meters per second south. Okay, next. Next, I'm going to go with this straight segment here. And I'm going to stop, I'm going to split this into 2 parts. When it crosses the axis, it's very different. So I'm going to split it into 2 parts. So in the green section, what's happening? Well, the velocity begins at -4, and the velocity eventually hits 0 meters per second. So right at that special point there, we have an instant. So instantaneously, what's the velocity at that point I marked? Well, it's 0. So 0 velocity means it's at rest. So it's instantaneously at rest. So how do you get from -4 meters per second to a stop? Well, you must be slowing down. Okay, so we're actually slowing down. Slowing down. All right, so I'll write from 0, no, not 0, from 2 to 3 point, I'm going to say 3.3. I'm just estimating here. It's still moving south, okay? So it's moving south because all the velocities are negative, right? It starts at -4, -3, -2, like all the velocities are negative. So it is still moving south, but it's slowing down. And I'm going to add, it's at a uniform acceleration because the line is straight. So the rate of change is constant. Furthermore, I'm going to calculate the number by calculating the slope. So slope is rise over run. Now the slope, I'm actually going to use the whole segment from 2 to 4 seconds because it's a straight segment, so it's going to have the same slope. So the rise, it went from -4 to +2, so the rise would be 6 meters per second. And the run from 2 to 4 seconds is 2 seconds. So 6 over 2 makes 3 meters per second, or meters per second squared, north. So it has an acceleration of 3 meters per second squared north. So recap, from 2 to 3.3 seconds, the object is moving south and slowing down at a uniform acceleration of 3 meters per second squared north. So you might ask, well, we calculated a positive slope, so a positive acceleration. Shouldn't that mean it's speeding up? No. The acceleration, being positive or negative, is only half the information you need to know whether an object is slowing down or speeding up. You also have to know which way it's going. If it's moving one way, but the acceleration is the opposite way, then it's slowing down. This is what's happening here. It's moving south, and the acceleration is north. So they're working against each other, causing the object to slow down. If, on the other hand, the object is moving a certain direction, and the acceleration is in the same direction, that's when it's speeding up. And that's what we see in the blue section here. In the blue section here, it still has an acceleration of 3 meters per second squared north. But it's speeding up this time because it's actually moving in the north direction. The velocity values are positive. So we're moving north. And then it's also got the acceleration as well. So it's speeding up. So in the blue section, the velocity starts at 0 meters per second, but then it gets higher and higher until it reaches 2 meters per second. So it's actually speeding up. All right, 3.3 to 4 seconds. It's moving north. Speeding up at a uniform acceleration, again, because it's a straight line. Of 3 meters per second squared. Okay, the next segment is a horizontal segment. So that is constant. Constant what though? This is a constant 2 meters per second. So we have a constant velocity of positive 2 meters per second. So constant velocity of 2 meters per second north. All right, so it's not at rest, it is moving at 2 meters per second. And then the final section, the function drops back down to 0. So it goes from 2 meters per second down to 0 meters per second. So that means it's slowing down, right? It's going from 2 meters per second to 0 meters per second. It's slowing down to a stop, actually. Slows down to a stop because it hits 0. It hits 0 meters per second. And the line is straight, so it's slowed down nice and smoothly. I'm going to call that a uniform acceleration. And I'm going to calculate the value of that acceleration with the slope. So rise over run. The rise is -2. It went from 2 down to 0. So the rise is -2. And the run from 6 to 8 seconds is 2 seconds. So -2 over 2 is -1. Okay, so that is how to analyze a velocity time graph. Okay, so these are all different shapes that you can see on the velocity time graph. So I'm going to try to quickly write out what all these shapes mean. The first one, we have a constant velocity at 0. Constant velocity at 0. So 0 means at rest, 0 meters per second. Then, one below it, we have a constant velocity. Okay, the velocity is staying at the same number, and it's a positive number. So it's going to be moving in the positive direction. Similarly, the one underneath that is a constant velocity again. It stays at the same number, but it's a negative number. Okay, the next one. So here the velocity starts at 0, starts at rest, and it's getting higher into the positive direction. So it's speeding up, and it's moving in the positive direction because all the velocities are positive. The next one, it starts in a negative direction. Actually, the velocity is negative the whole time. These are all negative numbers until it hits 0. So it's actually slowing down because it's hitting 0. It's getting closer to 0 meters per second. So it's moving in the negative direction and slowing down. And then the third one in this column is actually a combination of the two above it. Okay, so it's a combination of the two above it. So this one, it's moving in the negative direction to start, and then it stops for an instant. Right here, it stops for an instant. Then it moves in the positive direction. All right, and now the last column. So the first one starts with a positive velocity. So all these velocities are positive, and it's slowing down to 0. So we are moving in the positive direction and slowing down. Second one is got negative velocities. These are all negative numbers. And it starts at 0. And then it's getting higher and higher magnitude. So it's actually speeding up. And the last one is similar to the one beside it. It's just flipped. So this one starts in the positive. Okay, so it starts moving in the positive direction. Comes to an instantaneous stop. So it's slowing down. But then starts moving in the negative direction. So it speeds back up again, but in the negative direction. All right, and now the last one here. So we're going to take this velocity time graph that we analyzed, the same one, and we're going to try to draw a matching position time graph. Okay, so I'm going to start with the axes. Okay, so time, seconds. Now position, so that's D, harpoon, in meters. and I'm going to copy the direction of north. This goes from 1 to 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so how do you get position out of velocity? So one last thing that you should have learned in grade 11 is that displacement can be calculated by the area between the function and the time axis on a velocity time graph. I'll write that at the bottom here. Okay, so I'll start with 0 to 2 seconds. So if I drop an imaginary line at the 2-second mark, I made myself a rectangle. If I calculate the area of this rectangle, I end up with the displacement that the object moved during those 2 seconds. Okay, so the area of the rectangle is length times width. So the length is 2, and the height, I guess, is -4, because it went from 0 to -4. So the area, I would say, is -8. Let me erase those lines to make it clear. The area is -8. Okay, so when a displacement of -8, so on my position time graph, I'm going to start at 0, and I need to end at a position of -8. So I'm just going to make -8 here, and put a dot at -8 at the 2-second mark. Okay, now the next section is a triangle. So the area of a triangle is base times height divided by 2. So base times height divided by 2. So the base is about 1.3 if it went from 2 to 3.3 seconds. The height is -4 divided by 2, getting us -2.6. Okay, so the displacement is -2.6 for the next section. Now, when you plot that on the position time graph, it's from where we left off. So we left off at -8. Now I have to go a further displacement of -2.6. So that will drop me down to -10.6. Okay, so my next point is going to be at the point 3.3 and -10.6. Should have gotten a graph with like whole numbers to make it easier, but oh well. Then we have this really tiny triangle. It's a really tiny triangle here. Okay, we're going to calculate the area. So base times height divided by 2 again. So that will be, the base is 0.7. The height is 2. So base times height divided by 2. That will equal 0.7. Okay, so this goes up. This goes up by 0.7. So at the 4-second mark, I'm just going to go up a little bit. Okay, I'm just going to go up by 0.7. That's not that much, so just a little bit there. Then I have a rectangle. Rectangles are easy, it's length times width. So the length is 2 and the height is 2, so that makes an area of 4. Now I have to go up by 4 more. So at the 6-second mark, I'm gonna go up to about here. I'm just kind of estimating these values now. It would be better with graph paper. And then finally, this triangle here, base times height divided by 2. So the base is 2, height is 2. So base times height divided by 2. 2 times 2 over 2, that's 2. So I go up by 2 more. Okay, and I end up around there. Okay, so now I'm just have to join up these points. But it matters if you join them up with a straight segment or if you join them up with a curve. Because the first 2 seconds is a constant velocity, I'm going to join these up with a straight line. However, because the next section is slowing down and the section after that is speeding up, I'm actually going to have to draw curves. So I have to make it slow down, so it's curving, but then it comes to an instantaneous stop and then it has to start speeding up. So that should make a nice curve, kind of parabolic actually, part of a parabola. And that would be the slowing down part and then the speeding up part. Then from 4 to 6 seconds, it's a constant velocity again. So I can use a nice straight line there. But then the last section from 6 to 8 seconds, it's slowing down. Okay, because it ends at a stop, right? It ends at 0 meters per second, so it's got to be slowing down. So I got to draw a curve that is slowing down. So it's got to be rounding out to be pretty flat near the end. So that would be my best effort at position time graph. I only calculated a couple of numbers. I mean, I could have done a little better if I were to calculate, be more accurate in terms of the y values and calculate all of them out. But I just wanted to save a little bit of time. This is qualitatively correct, at least. So that was a whole lot. I'd like you to do the multiple choice questions on the Google form. And then I'd like you to read section 1.1 from the textbook and try the questions at the end of that section as well.